to introduce our seminar speaker today. It's Losic from Alberta University. As usual, academic history is quite young. He's very young. He did his PhD with Bill Unruh, whom some of you might know from the Unruh effect, of course. And he is an expert in conceptual problems in cosmological perturbation theory, very deep problems which we need to solve, first of all, in order to go to higher orders, but also to understand if the linear perturbation theory is actually consistent. And this will be the topic of this talk today. So welcome, and we're looking forward to your talk.
Thank you, Stefan, and thank you all for inviting me to this beautiful country. So in this talk, I've sort of purposely cut it a little short to allow for questions in the intermediate stages, so I kindly encourage you to interrupt me as I go along. So the basic plan of the talk is to cover nonlinear perturbation theory in sort of heavily relativistic cosmology, and also to look beyond that, to look at current theories, or just mention along the way some current ideas in trying to address some of the crucial issues that we're now facing with all the observations that are coming in. So cosmology is now in a period of unprecedented development, precisely because we can now distinguish between various theories. One of the major tools, theoretical tools that we have to make progress in cosmology is in fact perturbation theory. And so when one looks at theories of the early universe, inflationary cosmologies are fairly compelling. And one of the questions I want to ask is, are higher order perturbations, so perturbations that go beyond linear order in the stress energy that's causing inflation and the metric of space-time during inflation, when one goes to higher order, are these perturbations in some sense important? So in order to motivate that, I'll just take a step backwards and take a look at what slow roll inflation is, just very briefly to remind those people who aren't directly in the field, and also in a sort of general way define what back reaction might be taken to be. And then we'll dive into two basic concrete test problems which try to answer the question of, do these nonlinear perturbations during a period of early universe expansion actually matter? And a simple plausibility argument suggests that the answer is definitely yes. And a detailed calculation also says that the answer seems to be yes. Not only that, but it seems as though these nonlinear fluctuations, namely the effects of the gravitational field, seem to be very important in all infrared modified theories of gravity. So that's what I intend to walk you through. If you are interested, a lot of this is contained in some papers that were published with Bill Unruh and an upcoming one, and some other stuff with Cedric Defayet. So again, please stop me if things are unclear. So one of the miracles of the early 1980s was imagining that there was a mechanism to basically slow down the creation slow down the rate of creation of space at early times to such a rate that the universe could thermalize at early times and still have a causal explanation for that thermalization. In order to do that, you have to have pressure to do work on the universe at very early times. And it can't be positive. So there has to be this sort of repulsive stress energy. So when pressure is roughly negative minus the energy density, and you get space being created at roughly an equal rate, energy density being roughly a constant, and the actual space is being created at roughly an exponential rate. In order to affect this, in order to make this happen, what one imagines is a scalar field driving this. And so typically, in the most simple models, what one has is a scalar field called an inflaton rolling down a very gently tilted potential. The tilt is gentle in the sense that the velocity of this field is the second derivatives of these, the second time derivative of this field is much, much smaller than, say, the potential energy. Or rather, the velocity squared is much smaller than the potential energy. When this happens, when this field slowly rolls down like this, it actually has quantum fluctuations in it. And these fluctuations mean that different points in space will have a scalar field decaying at a different time. And so different points in space will have the scalar field reach its minimum at different times, and this will then lead to classical energy density fluctuations, which, if you believe the Einstein equations, which relate the stress energy to the metric, induce metric fluctuations. That is to say, fluctuations in the space-time metric itself. And so the idea then is to try to solve the equations of motion, namely the Einstein equations, in a successive power series in these fluctuations. And so the miracle of inflation is embedding a classical explanation for why the energy density doesn't diverge as you go backwards in time using the standard Big Bang equations, with a mechanism to generate quantum fluctuations. Okay. But also, it's of course one of the key problems, because if you put this equation of state into the, if you want to generate a stress energy with that equation of state, you quickly realize that all inflationary models are actually past geodesic incomplete, which means that they need more physics than just inflation to explain the initial conditions in the universe. But that's just mostly for experts. Okay, so second order inflation, second order perturbations in slow roll. So what you do then is just very naively take the scalar field and perturb it to first order, for example. And so you know that since the stress energy for a minimally coupled scalar field is basically this binomial form with a potential term, you know that just naively, if you take this scalar field in the background and you take it slowly to be a constant, then the background field with the potential constant, the background stress energy will go to 0. Since this is quadratic in the field, the linear order term will go to 0, as this is slowly driven to be constant. And so at some point, when this thing is constant enough under heavy quotes, the second order terms will become the dominant term and the leading order term in this expansion. And so the question then naturally becomes, is there a transition to nonlinear dominance, i.e. when will the nonlinear terms in this field equation start to become important for the gravitational field? Okay? So then the question is, where is that transition going to occur? So that's one basic and general question that you can ask. And in particular, the most radical possibility would be that that's precisely when the slow roll condition holds. So the slow roll condition, if I can just go back for a second, is precisely that this scalar field rolls slowly enough such that inflation not only takes a long enough time to erase all the inhomogeneities that have occurred and so on, but also to give you the right amplitude of fluctuations. Okay? So then the question is, when this background scalar field, because you can see here that this guy right here will be a background scalar field gradient times a perturbed guy, when this background term drags this entire combination down to a very small value, will that coefficient be of order of the slow roll parameter before this guy starts to become important? In other words, when do higher loop effects come into play? So just to give you a broad idea, it's easy to write things down, but then when you try to calculate them, it's a bit of a mess. So just figuratively, just to give you an idea, if you write down the line element with these full second order fluctuations, then what happens is that at linear order, you can decompose fluctuations in terms of scalar fluctuations, things that basically have a helicity 0 or a spin 0. Similarly for vector and tensor. Of course, we know that the tensor fluctuation is fundamentally a spin 2, but it's convenient to decompose it at linear order. It's actually certainly always unambiguous. At second order, however, these things mix, and there's no clear way to proceed, so such a classification actually fails. So generally, through the second order, you keep the entire metric without decomposing it into various parts. And you can ignore these little labels. And similarly for the second order scalar field. So that's what you put into the full Einstein equations, and then you try to solve for all the amplitudes. So it's a bit of a mess. The one final detail that you need to know is to say, okay, the actual potential that this inflaton rolls on has to be very slightly tilted. And so for first approximation, what you can do is just say that it's a constant plus a very small tilt in the actual scalar field. We can even have that tilt to be linear. And so then one measure of how shallow that potential is in fact the slow roll parameter, which you don't need to know in detail, but just to sort of figuratively know involves the gradient of the scalar field potential divided by itself squared. And with that value, the scalar field indeed rolls down extremely slowly. So with these assumptions for the background model, you then try to perturb about that. So again, figuratively writing it down, what you find when you go into, for example, momentum space or Fourier space, you find the linearized equations of motion. So linear order, the picture is mathematically very well understood. These Fourier modes travel oblivious to each other. They lead to a very well-known theory of cosmological perturbations and so on. At second order, however, it's very interesting. First of all, there's a couple of new things that go on. Like I mentioned, there's tensor and vector fluctuations, which actually can source second-order scalar fluctuations and so on. But the main idea is that the right-hand side here, so this is like the linear operators acting on the second-order metric and matter fluctuations, is actually cumulative. So what that means is that, for example, during inflation, the Hubble radius is actually shrinking during inflation. So it means more and more modes are exiting outside of the Hubble radius. So it means that the infrared phase space, in some sense, is getting very, very large. So that means that these integrals right here actually have the possibility of getting extremely large. And in fact, large enough to suppress, to overcome the fact that they're actually suppressed by this order epsilon squared.
So I'm not to slow down, just a question. I mean, in linear order, I do basically this decomposition in helicity 0, 1, and 2
Sure.
in order to construct gauging quantities and derive for them actually equations of motions, which are
Sure.
generated. So how do you proceed here in the second one?
Well, I mean, you can isolate the second order sector and say for a given second order scalar mode, these tensor, vector, and scalar combinations will contribute. But the point is that on the right-hand side, you can't meaningfully decompose them.
So so there's no gauging formulation?
No, there is. But the point is that the combinations that enter them will always be of mixed felicity.
Oh, okay, but that's fine. That's
Yeah.
fine. Yes.
These problems you discussed, are they common to expansion around the slow roll and expansion around the city?
That's a very good question. In fact, I'm going to address that in the next couple of slides. There actually is a big subtlety between slow roll and Losic. But both, I hope, are exciting to you. So please ask questions if anything is unclear. But you can see that it's a bit of a monster to jump into. So then, where there's a monster, there's always controversy, right? So this is not by any means a new subject. People, long ago, Emil Mottola, Richard Woodard, and even recently Steven Weinberg have been asking certain questions about this. And so one of the key questions, in fact, is, can infrared, by which I mean fluctuations on a scale larger than the Hubble radius, and K here is just the co-moving wave number, and H is the Hubble scale. Can these backreactions alter de Sitter expansion in the sense of renormalizing the background cosmological constant? Okay. In fact, people like Brandenberger and so on have suggested that there might even be a late-time dynamical relaxation method for cosmological constant, a time-dependent backreaction method that actually drives it to zero. Like I said, recently there have been questions about two-loop effects depending not on the sort of the end point of the modes entering or exiting inflation, but also the entire history of the modes. So, there's a lot of contention here. I'm not going to discuss any of that. There's also similar effects that could actually alter slow roll models, including reducing the actual period of inflation that the model can experience. So, for example, if inflation proceeds, then these nonlinear fluctuations could act in such a way that they actually reduce the amount of time, they actually speed the scalar field up in its sort of journey to the bottom of the potential, and actually slow down rather actually shorten the actual period of inflation to such a point that you don't have enough to solve all the classical problems it was designed to solve. In my talk, all I'm going to do is focus on the most radical possibility, namely that the back reaction itself, these second-order effects, dominate in their effect over the gravitational field during slow-roll inflation. That's the most radical possibility. So, I mean, this could imply a number of things, namely just simply the breakdown of perturbation theory, or it could, in fact, provide one of the first glimpses of perhaps eternal inflation. So Linde, for example, always draws these pictures. Is there chalk here? There's chalk. So the common picture here, so if you have these chaotic inflation models, okay, so what they do is they commonly draw these pictures of basically implying large-scale nonlinear effects, where these guys, these nonlinear effects, push the scalar field up to potential and then have these little self-reproducing domains which continue to inflate. Unfortunately, none of that is really reinforced by strong calculation. So what one needs to show is that large-scale nonlinear effects actually do occur. So that's one of the hopes, that we may be going in that direction. Of course, we can't solve the full problem since we don't have quantum gravity. Okay. So what we do is we're forced to do effective field theory. So what that means, in effect, is that we're cutting out the very important link between ultraviolet back reaction, so back reaction within the Hubble radius and down to some amazingly small scales, and the link with infrared back reaction. So we don't know, and the links here are basically contained in what we call observables. So what I'm going to do is focus only on infrared back reaction. So that's the condition where you have the wave number over the Hubble radius, co-moving Hubble radius, much less than 1. And I'm going to focus on some peculiar difficulties that appear with this problem. But just to reinforce what's actually going on at second order, this isn't that for a given actual mode at second order, a whole swath of linear modes contributes. So it's this cumulative contribution which actually gives one hope that there's going to be a large effect. Okay? And so this integral here is nothing more than the second order source in the field equations that I wrote before. If I just go back for a second. Here we go. So this mode, this source for the second order modes, which I'm claiming can get relatively big compared to these guys, is actually what's going to be driving this. And this is just a diagram showing that I'm going to be integrating the source from some infrared cutoff, or rather from the Hubble radius, up to some infrared cutoff. Okay. When you go through and do it, I'm going to spare you the details. When you go through and do it, you find that you get tremendous problems. I can summarize 3 of them. Well, first of all, let me show you the picture. This is what I felt like when I was doing it. So this is, I guess it's not me, but I mean, it's somebody, I guess, doing this problem. And this is the linear problem, and then you sort of open up the Pandora's box of the second order stuff, and out pops all this stuff. So you can see it's sort of an infrared problem as these ghosts and goblins sort of expand out to occupy most of the space. So one of the key things that you find is that in your equations of motion, you can have a ratio of small parameters. So that means that, mathematically it means you have a non-analytic series, but it also means that you can't really throw these terms away, just on a very generic ground. So that means, for example, if you're looking at a long wavelength sector, that a very small term divided by this term, which is the slow roll parameter, which basically tells you that you're in an inflating space-time, can be either big or small. So you don't know what to do with these terms, and they cause you problems. There's also a huge problem because the fluctuations themselves are so large that they feel the curvature of space-time. So the curvature of space-time is so, it's on a sufficiently small wavelength that they actually feel it, and that means that they become gauge dependent. So that means that you may solve the equations of motion, but your answer could just be some sort of coordinate effect. You may not be describing physics. And that's a general problem with general relativity or any generally covariant theory where you try to do perturbation theory in it. So, you know, at the end of the day, you're faced with this giant mess, and you don't know if you're getting something, you know, that's physical. So one way to proceed, and this is the plausibility argument that I hope to show you, is that you observe that the universe is almost de Sitter both today and apparently in the distant past. So if we just recall that de Sitter spacetime is actually a solution of Einstein's equations, which is remarkably simple. It's just a positive cosmological constant. It's expanding everywhere, in the distant past and in the distant future. So for those of you who aren't familiar with it, an embedding diagram of de Sitter spacetime is like this, and each one of these constant moments of time, E equals constant, is a three-sphere. So it's like a sphere, except with one more angle. As it's embedded, it's actually got one more angle. So this entire space-time is actually spatially closed. And this is called the de Sitter solution. Now, inflation is actually different than de Sitter, but what we can observe is that they're basically all perturbations of de Sitter space-time in some sense. So we want to investigate the case where you're doing perturbation theory near de Sitter space-time. So in order to proceed, what you realize is that you just take a step back and you just to remind you that general relativity is a constraint theory. So you have you write down the Einstein tensors proportional to a stress energy. That's the Einstein field equations. But you can write down also these equations in a Hamiltonian form. And the Hamiltonian form guarantees basically that 4 of these equations are so-called constraint equations. These constraint equations are the heart and soul of the theory. For experts, you know that they generate the diffeomorphism variance of the theory. But for us, just to look at it, when you perturb these equations, what you find out is that they're elliptic differential equations, which are constraints. Okay? But we already know what these guys are from E and M. Okay? So if we take our favorite linear theory, then we know that the Gauss law is an elliptic initial value constraint on the evolution equations for the electromagnetic field. So this is a constraint on the initial data for the actual propagating electromagnetic field. So what we can do is write this down, and let's imagine that we're writing it down for a closed space. Okay? We decompose the electric field into a transverse and longitudinal part, and we obtain a Poisson equation, that is to say a Laplace equation with a source. And then we ask under what conditions can we always solve this equation, given that we live in a closed space. So then what we do is we find that, for the mathematicians in the audience, to invert this elliptic operator, you have to have the source orthogonal to the kernel of the adjoint. But I mean, what you want to do is you want to guarantee that the total charge is 0 on a sphere or on a closed space. But here, for example, if you proceed formally, what you do is you say, in order to invert this guy, in order for me, for any rho, to find a solution for phi, all the harmonic functions of this guy, so all the guys that have Laplacian h is equal to 0, better be orthogonal in the measure of this space to rho. And since all the harmonic functions of the Laplacian on a closed space are just constants, I pull them out of the integral, and I realize that the total charge has to be 0. That's the condition that that equation always have a solution. That's called an integrability condition. So in other words, the source always has to be orthogonal to the harmonic functions of this operator. Now, why do I go through all this sort of jargon? The idea is that the exact same thing happens in gravity. Okay? For the linearized constraint equations, order by order, you can ask the same questions and receive very similar answers, that you need to have these conserved charges. So let's just take a step up and go to an Einstein static universe. So when Einstein was first working on cosmology, he tried to reconcile his philosophical prejudice with the universe being static with his new theory. And the way he did it was he generated a solution where he had a fluid precariously balanced by something he called a cosmological constant. The space-time was static. Its geometry was like a slice of time from de Sitter. It was just a three-sphere sitting completely static. And a couple of years after he did that, Eddington showed, famous British astronomer, that it was like a pencil sitting on its edge. It was very unstable. Okay. About 5 years ago, George Ellis came to UBC and showed us some results that showed that if the pressure was sufficiently high in the Einstein static universe, you could have inhomogeneous modes, inhomogeneous fluctuations, which actually had a Jeans wavelength larger than the scale of the universe itself, which meant that all those fluctuations were actually stable. Okay? So Eddington showed that for pressureless dust fluctuations, of course, the universe is unstable. The Einstein static one was unstable. But what Ellis showed was that for large enough pressure, these modes were actually going to be stabilized. So we got curious about this. Is it really true that Einstein static is actually stable? And so what you find is, if you go through the entire same exercise that I showed you with the electromagnetism, except instead of these equations, you have the initial value constraints for general relativity. What you find is a constraint of this form, a charge, with some other details that I won't explain right now. A charge is equal to 0. What we find is that these so-called stable modes must always be accompanied by Eddington's unstable mode in order for this charge to be exactly 0 because of the nature of the constraint. So what that means is that even though linear perturbation theory will tell you that you found a stable solution, a dynamically stable solution, what you find in the end is that linear perturbation theory is actually failing you because through the second order, these solutions are not integrable. They're not actually going to be real solutions to Einstein's equations. I see a lot of really, really amused looks. So let's see, is there an eraser here? Yeah. Oh, is that? This is the eraser?
You can pull down the other board, that's simpler.
Oh, okay. That seems simpler. Let me just continue my thought and I'll give you a simpler example. So if we imagine that we've solved, take it to the Einstein's theory or any theory at all, some theory with a parameter, say lambda. And we don't know how to solve any of the equations in the theory, but we know how to solve them in a very simple case, say for perfectly homogeneous and isotropic conditions. So then we do perturbation theory about this because we have no idea what the bridge structure of that solution is. We know that our solutions of the linearized equations have to be tangent to the full family of solutions. Otherwise, there's no sense in which we're approximating that full family of solutions. What I'm telling you in this slide here is that if you had taken Ellis's modes, those modes would actually not be tangent. They wouldn't be integrable. Now what actually happens is you have to consider these charges as further necessary conditions to ensure the geometric property that this is an integrable series. Here's an even simpler example. If I take x squared plus y squared is equal to 0, and so I don't know how to solve that equation, find the real solutions to this equation. Okay, then I do perturbation theory. So I take 2 x bar delta x plus y bar delta y is equal to 0. If I know the background solution is x bar equals y bar equals 0, then that means that delta x and delta y can be arbitrary. But we know that that can't be the case. We know that the full real solution is actually x equals y equals 0. This is what's known in the literature as a linearization instability. And it affects all nonlinear field equations in certain situations.
So, can I just ask you, because there is a well-known result, as you know, I suppose, that the Einstein equations are linearization stable if there are no symmetries.
Yes, but we're doing perturbation theory about symmetric solutions.
Yeah, right. So, I mean, okay, let's keep it just
Sure. No, I'm aware of those results. So then the idea is to go through and try to see, in the Slorol case, where one has fewer isometries but still some isometries, what the actual conclusions we can make just by sort of cheating, not doing perturbation theory but still doing it at the same time. So in that case, what I do is I take the Einstein field equations, and once again I write down the constraints. So the constraints are initial value constraints relative to a certain structure in space-time that's called a foliation. Just how I slice space-time. And what I do is I ask, what are the charges associated with this? What are the projections of these constraints along a certain direction, along a certain vector field? And we know that when this is a special vector, namely a killing vector, then these projections are exactly zero. So then the question is, in a slow roll case, can this help us? In particular, can it tell us what the second order fluctuations are doing when we get close to the slow roll case? So we pick a particular projection we want to look at, namely this so-called boost vector, and we, instead of looking at the actual cosmological perturbations, we organize the fluctuations in terms of these actual integrals, these projections. And what we find is that when we go through the second order, and we take, this is actually wrong, when we just take the slow roll parameter to be of order, whatever it is in these current models, 10 to the minus 2 or 10 to the minus 3, what we find is that generically, the integral part of the second order fluctuations dominates that of the quadratic combinations of the linear parts. And there are two immediate bonuses. It's a gauge invariant statement, and it really does seem to be showing us that there's something nonlinear happening during slow roll. So let me just take a step back and give you the take-home message from this slide. The message is this: if you take the Einstein equations and you feed them the standard inflationary assumption that there is a slow roll going on, and then you take the perturbative expansion to second order and expand the constraint equations in terms of these projections, what you find is that on generic grounds, the second order pieces of that series will always have a larger amplitude than that of the quadratic parts of the first. So that is a strong signal that there is something actually going to be happening when you take these constraints and evolve them forward in time. That gives you strong motivation to proceed. Okay, so all the difficulties that I laid out before in the previous couple of slides can actually be overcome, and there's actually something, nice. There's a pot of gold at the end of the rainbow or something like that.
And will that be generic to all orders?
Sorry?
Will that be generic to all
No, I'm
orders?
only considering up to second order. All orders we don't know.
So that in what sense is this relation gauge? On the
In the
right-hand
sense
side,
that-
you have a billion gauge shift symmetry. On the left-hand side, you would have to expand the gauge symmetry to second.
No, well, both are invariant. The point is this. There's going to be a prefactor here, which goes as 1 over a slow roll parameter.
Okay.
And so if you tell me, find me the worst gauge transformation that can remove that, the answer is that there are always factors on either side of that gauge transformation that cancel exactly. And I'm always left with an extra factor on the right-hand side. In that sense, literally, it's gauge invariant. So it's invariant under second order fluctuation, second order transformation.
So
Not under third order.
Oh, okay. But you expand basically on both sides. I mean, the gauge here, or any phase space variable here on the left and right-hand side, is invariant with respect to second order gauge transformations.
This is, yes, this relationship is invariant right down under second order. So that's sort of the plausibility argument. It's probably hopefully giving you some confidence that when we wade into this, it's actually going to give us a result. So just to remind you again, now I'm actually going to do an actual calculation concerning evolution and try to figure out if these second order effects are actually getting big. So we put in the potential. Again, it's just a slowly rolling potential. The scalar field is slowly rolling. The space-time is expanding, almost exponentially. There's only one non-trivial slow roll condition, which is just this v prime squared over v. And the scalar field just slowly decays. Okay. So again, I've gone through this. So what I want to do in the end is to extract some sort of series in the equation of state. So if I want to figure out what the space-time is doing, then what I do is I try to write down an expansion for the energy density. So I have a background term plus a second order, or a first order contribution from the first order perturbation theory, then I have a second order contribution. Okay? But these are cumulative, as I mentioned to you. And that's the reason that I hope that they can overcome the fact that they're actually suppressed. And similarly for the P. that's sort of the goal of the game. And then at the end, yes?
So sorry for interrupting again.
Sure.
Just to understand what Hector asked, could it be if I would go to third order that all the conclusions you draw at second level?
Are erased?
Yeah.
Well, that's not
Maybe
even realized
because
theory.
No, because in some sense you are saying, that's not clear. Like, I mean, because in some sense you are saying, in order to get equability to lower order, higher order kind of constraints, restrictions become important.
Sure, sure.
So
But,
it's not, yeah.
but the point is that if you're only interested in the linear sector, then it is a provable statement that only the second order constraints come to constrain the linear order sector. If it were true that an infinite hierarchy of third, fourth, fifth, and sixth order constraints constrain the first order solutions, there would be no solutions.
That's right.
So, I mean, but that's the classical linearization and stability argument. This is slightly different because I'm away from actual pure de Sitter, and I'm using these kind of quasi-isometries and so on. I don't want to complicate it, but I mean, it is not true that the third order and fourth order are going to have any further effect on the question that I'm asking. But are they going to be altered by considering third and fourth and high order? I don't know.
So why can't the charges you derive in third order, say, or in fourth order, can't they change the charges you got in second order?
The charges that appear on the second order
Yes.
are going to be multiplied by first order charges. Okay, and then there's going to be first order charges cubed, and so on. And we know how those behave on the source. So I can't see offhand how. So then, what do we want then at the end? We want to say, okay, we have this first order quantity and this second order quantity and the stress energy, and we're going to use these quantities to see what is actually happening with the gravitational field. And what we'll do is demand, you can ignore this comment, we can demand that the dispersion of the pressure, so we know what the order of magnitude of this is by CFE, it's 10 to the minus 5, must dominate that of the second order dispersion. And so then the question is, in order for this relationship to be true, how close to de Sitter do I have to be? In particular, do I have to be at slow roll? So that's really the crucial point. Okay? So how do I find these pressures and energy densities? Just throw this out. What you do is you find total stress energy through the second order. You can define them as the eigenvalues of the mixed valence stress energy. It's a bit of a mess. You can do it constructively as well, and so on. I just kind of throw this out because through the second order, you have to deal with unique problems like subtracting the isotropic pressure contribution from shears, and so on. So it's interesting. This is explicitly showing you how gravitational waves shear in such a way that they contribute to second order scalar modes and so on. So that's an interesting thing that appears at second order. But in any case, you can calculate these eigenvalues, and then we go and try to calculate those expressions. So since these are quantum fluctuations, you expand the basically what in the literature is called the Mukhanov variable. It's a metric fluctuation. In terms of these, just the standard creation and annihilation operators. And what you try to show is just try to find these fluctuations in the actual operators. So you use Wick's theorem to go ahead and find these things. And you go through it. And in the end, what you find is this dispersion. The only reason I throw this up right here is to show you the difference between previous calculations and this one. This term right here was used in previous calculations due to Brandenburger and so on, and Weinberg. These additional terms appear if you insist on retaining the second order sector. And the interesting thing is that if you retain those terms, they actually give you the dominant contributions in the final answer. Okay? So then what turns out, I mean, the details are important, but I want to show you the methodology. The bottom line is that in order for this condition to hold, the requirement on the background is that the slow roll condition be violated. Or conversely, whenever the slow roll condition holds, the second order fluctuations must dominate in their effect on the vector. That signals either the failure of perturbation theory during slow roll inflation, or it signals that there is something fundamentally non-perturbative going on in the sense of eternal inflation, which I guess could be the same thing.
So sorry, can I understand what physically happens here?
So physically, this is the picture. Inflation is going on. The Hubble radius is actually getting lower, smaller and smaller and smaller. More and more modes are exiting. The infrared phase space is growing much, much bigger. This is then leading these integrals, which are appearing in the equations of motion, to diverge. They go as logarithms of k. And as k gets smaller and smaller, it goes as k over ah, and k over ah is getting much smaller. So then basically what happens is the terms of the stress energy with these guys get non-perturbatively big, but this is different than the usual infrared divergences that one encounters. The reason it's different is because you can change the infrared cutoff all you like, and that dependence drops out. Okay? And it's also very different than the usual stuff you find in de Sitter because there's a finite departure away from de Sitter. So this is not exactly the usual divergences that you would find that were found about 25 years ago for actually de Sitter space time. This is actually a divergence in the stress energy, which appears to be not only caused by the fact that you sort of assume slow roll, but that you're only assuming one part of the fluctuation sort of contributes to the stress energy, namely the infrared. We don't know the answer to the UV question yet. Okay. So if you were to ask, can I observe this stuff? The answer is no, this is a toy problem. It's a suggestive direction. But we don't know the answer yet of how to actually calculate what an observable effect of back direction would be. Okay. So this is part of the answer from general relativity.
This is true for all the parameter space that is still
The parameter space that we're considering just for the slow roll condition, just for this scalar field very, very slowly rolling, then it's true.
You describe some of the background is in closed space.
Yes.
How important is that?
It's fairly important in the sense that when you write down these constraints, these charges and so on, they are constraints because they're actually equal to surface integrals, which you take to be zero when there's a closed space. However, when you're in exact de Sitter, there's no controversy about that at all, because it's a closed solution.
Why would it be exact?
Huh?
Yeah, why would it be something like
You're not an exact de Sitter solution, but you can consider these surface integrals. Also, some sort of boundary terms, boundary condition terms that happen during solar inflation. You can actually successfully argue that they are zero. If you set the actual values of the fields, you can show that since the metric is arbitrary, since the Bianchi identities are satisfied for an arbitrary metric fluctuation. We can discuss this in greater detail later. You can actually arrange it such that the stress energy, the contribution in that boundary term, goes uniquely to zero. It's a little more involved.
So sorry, say all this work which has been done on boundary effective is going to address superplankton physics and all that stuff. This is then essentially all wrong, right? Because they were more worried about UV completions, but you say they have not figured out the main problem lies in the infrared.
Well, I don't know if it's wrong because I don't know if this is right. So, yes, I think it's dangerous to ignore the fact that there seems to be a problem. That's all I can say. Yes.
Why did you say this was not observable?
Sorry.
Why did you say that this did not have observable?
Sorry, I can't understand.
Why did you say that this did not have observable effects?
Well, because these modes are outside. I mean, they look like homogeneous. They look like a normalization in our scale factor. You know, we don't know. You can't. I mean, it's like saying what is the cosmological constant in our solar system? We simply can't observe it. It's something that's much larger scale.
Sorry. We know how to calculate the probability spectra for the perturbations, the first order.
Yes.
Using equation variables and so on.
Sure.
But for this second order, how can we calculate this spectra?
The spectra,
Yeah, for the perturbations.
you mean calculating
P of K.
non-Gaussianities and things like that?
I
Or-
mean, just P of K. I mean, just having that shape of the spectrum.
Well, I mean, formally you would go through this similar sort of exercises, but of course the power spectra are very different because you're not inflating today.
Correct. But do we have any invariant variable here? Like
So that was
theta
Stefan's
and-
original question.
Yeah.
So the scalar vector tensor decomposition fails
Yeah.
at second and higher order. So then you can have these variables, but they're always going to involve spin 2, spin 2, spin 1, spin 1, spin 0, spin 0 combinations in these things. So you can construct it.
Okay, that's a good point. Rashan is asking. So, say, could it be that I cannot probe this infrared nodes, and that's finally the reason they would never couple to any metric field or any energy moment in terms of depending where you consider the infrared problem. I could never see these.
No, that's not true, because we know that when inflation ends, the Hubble radius gets much bigger. So all the stuff that left comes back.
Yeah, but then
So then there are imprints of this stuff.
no, once they are in, right? Why do I have an infrared problem here? Once they are on some horizon scales, I don't see infrared problem.
You don't see, well, we don't, I mean, well,
Yeah,
it depends. We see an obvious infrared problem in the sense that we don't understand what 90% of the energy content of the universe is. But
No, but that's right. That's why I agree with that. Of course, I won't accept that as an answer. No, but I was just asking: is it clear that I can construct an observable which could probe this IR divergence? It's no problem having divergences as long as I cannot couple a detector to them. Right?
well, see, that's part of what we talked about yesterday. I mean, there is this. I mean, one of the fundamental thing that astronomers measure is the distance-luminosity relationship. Okay, and this is a strong dependence on the redshift, which in turn depends on the metric and so on. So one can actually try to find a relationship between these infrared back reaction effects and something that one can measure within one's own Hubble bubble or radius by using these such relationships. Because then you know the dependence on the space-time expansion with these metric fluctuations, these distance and luminosity fluctuations. So it is possible to construct these variables. That's part of the exciting sort of future work that one needs to look at for this. I'm not sure if that actually answered your...
Well, I would say that I totally agree that this is super important to do. I just was wondering if it's clear that I can couple, let's say, any detector to something which is sensitive to this IR problem.
Well, we don't know the answer because we
But
don't
it
have...
could be that we can't, and then it's not clear to me if it's really a problem or not. That's just what I'm asking.
Well, I mean, it certainly does mean on a formal level that you can't use this kind of perturbation theory.
That's right. Yep.
So that's just not going to work.
That's right.
So that means that all the conclusions that we reach for some slow roll models are actually simply wrong.
Well, as an effective theory which stays above this infrared singularity, I can. If it's really decoupling in the sense that I can't find a current or whatever which couples to the IR problem and I stay away from this singularity, then I should be able to come up with an effective description of perturbations. That's what we always do in the UV, right?
But okay, well, we don't know. We don't actually know what's going on here because I mean these are non-local effects due to the quantum fields. Yeah, so we don't know if field theory will work. But are there loopholes? I mean, you could say, okay, well, who cares about this potential that I used? If I use a chaotic inflation potential, do I get the same answer? And if I do use a different formalism, then I do get the same sort of thing. Is it a gauge-dependent result? No, it's not. It doesn't appear to be. So then, one of the recent things that have become popular in gravity and so on is to take Einstein's equations and modify them for large distances, to try to take into account dark energy or things like that. And one of the most famous models is the so-called DGP. I'm just going to briefly describe to you what a very similar problem that appears with that model. So if you just imagine the picture of the space-time that I drew before, it's just a de Sitter space-time, but imagine that it is itself embedded in a flat space-time called just Minkowski space-time. If I do perturbation theory on this de Sitter space-time, embedded in this situation, then what I find is that there's a continuity equation for the stress energy of that bubble in the and the flat space-time, and also this Hamiltonian constraint that I mentioned before. If I combine these two equations and expand through to second order of perturbation theory, then I arrive at a very similar sort of looking constraint, an integral kind of constraint, which has a very kind of curious resemblance to a lot of this other stuff that I've been talking about, namely that if I take a look at that equation, this is an equation describing the embedding of that universe in a flat space-time, a higher dimensional space-time, then what I find is that if I go to Euclidean space, so if I take the time in de Sitter and change it to a Riemannian coordinate, I find that there are no allowed fluctuations at all allowed on this, basically this de Sitter brane. So let me just, the take-home message for this is, if I want to do quantum gravity, if I want to use a path integral on a de Sitter universe, which is embedded in a flat space-time, I cannot do that because there are no allowed fluctuations in the Euclidean space. So
Do you
then
have a physical explanation?
the physical explanation, I don't know. We don't know the reason for this. I mean, we only recently found this. I mean, I don't actually know what the actual. I mean, one physical reason is that it could just be wrong.
That's the base.
It could just be an indication that the theory is on very, very, it's in quicksand. But we don't know. We don't know what the actual reason is. You could ask similar questions for scenarios such as what Stefan has been working on before, known as degravitation and so on. And it appears as though similar constraints exist. And the bottom line is that any infrared modified theory will always have to contend with being consistent with these sorts of global charges. And that presents an interesting way to classify infrared modified theories of gravity as whether or not they're consistent with these constraints or not. So basically, yeah, so I've gone through this. Basically, so the consistency condition would be not only to solve the leading order constraint equations for the fluctuations, but also these second order constraints. And perhaps for our next talk, I can talk about the actual quantum story. It's actually very interesting in the sense that it brings back all the common problems that we've forgotten long ago from general relativity, including the problem of time. So I'm going to leave it for questions, but these are my conclusions. I hope to convince you that these second order perturbations do actually get big. They do become important on general grounds when you simply assume the usual assumptions for slow roll inflation. They seem to persist in importance for models such as DGP or degravitation. And the bottom line is that ordinary general relativity, coupled to an ordinary scalar field with no extra dimensions or no extra stuff, is still largely unexplored and has a lot of surprises left for even just scratching at the surface at it. So, well, thanks for your attention.
Yeah, thank you very much for this. So we have still a little time for further questions, Hans.
I have a general question. These in quantum field theory, all the examples I know of when you encounter infrared divergences, like be it Kondo problem or be it QCD jet production or QED, you always try to find some kind of summation scheme and see if you can find some, some protected set.
Sure.
Is that something that?
Well, I haven't thought of that, to be honest with you. It doesn't appear. I mean, by resummation, that would basically correspond to changing the background in this perturbation theory. So, for example, if I took the background as what I called the classical background and the linear fluctuations, if I took that as a mu metric and tried to repeat these calculations, you get the same answer.
Although, of course, in many examples, these kind of resummation might give you non-trivial changes.
It could be.
Like, there are famous examples of that.
Sure, I know. But for the example that I've tried, it doesn't appear to change the answer. So I'm not sure. I'm not sure how much that spans the space of examples, but I've tried.
Further questions?
When you have infrared problems in a space-time and space is closed, the infrared comes from integration over large ions.
Well, no, these are just surfaces of constant time. This is just
Three
the
So
initial.
what's the problem symmetrical when
They're just
it's in your
initial.
closed space?
Right, I have a spatially closed space, for example.
Why is it divergent from space?
You know, so the actual, so just for the de Sitter space-time, for example, pure de Sitter, there are no, I mean, there's a standard set of infrared divergences, but these are in the tensor modes. They're not in the, there are no scalar fluctuations in de Sitter. It's a vacuum solution. So it's, I mean, there's the standard Allen and all these other guys in Mottola have looked at the infrared divergences in the transverse traceless sector. Okay? But in the inflation case, what I'm looking at is not a divergence, but what the relative amplitude of the two terms is. Okay? It isn't that this guy is going to hell, it's he's going to hell relative to.
Yeah, fine.
So how can we in fact compare this result? I don't know with the observation. I mean, just we should calculate the spectra, or I mean, what's the way?
So the ultimate way would be, I think,
The spectra.
to look at sort of what I actually described as these fluctuations in the luminosity distance relationship. So these things should actually produce pockets of space which expand at radically different rates, and this should have a strong spatial dependence.
Yeah, that's correct. But for the early moments, early universe. For example, its effect on the inflation theory.
Well, what this is, we're assuming inflation when in fact this is showing that inflation isn't
Yeah.
working. Right? So it could well be that, inflationary theory is simply, at least a slow roll theory with a scalar field, may not be the actual correct answer. One can get scale-free spectra by assuming all sorts of different things. You don't need inflation for scale-free spectra. You just can't get them as natural. It's just so. The real answer is, can we generate some way in which to create an observable for subhorizon physics and connect it to how these infrared guys go? We don't have the answer for that yet.
So just 1 minute. If you discussed yesterday this work by Ruth Duro, she calculated what metric fluctuations would do to the luminosity density, right? So you're saying that if I would go to higher order in that calculation, could it be that I can generate modifications that will have an impact on the luminosity density such that I could, in the worst case, erase the cosmological constant?
I guess, yeah, it depends on your point of view. I guess in the worst case, you could erase it. Yeah, definitely. There's really an open book here. Because finally we now have the technology to deal with interacting quantum fields in a curved space due to recent work.
Well, wait, now you get to figure it. Are you saying that spatially I can have a look at pockets in space which would have no cosmological constant and pockets that wouldn't? Is that the way? I'm trying to understand how should I take home your message here? Did you say that it could be some directions? We're talking about spatial in homogeneities and that you
Right.
erase the cosmological constant.
Right.
Are you suggesting that it's conceivable that you have some direction in the sky where you can see effectively no cosmological constant and other where you would at a 100% level?
I can't rule it out, if that's what you mean. I think it might be possible. I'm not exactly sure.
It was not meant as a provocation, but as a project.
No, I think it's great.
No, the problem I didn't understand, I didn't hear provocation.
No, because he is observing the supernova, not you.
No, it's exactly the kind of questions we're trying to address right now, whether the spatial variation is interesting to look at. So therefore, I'm
Well, if you find something, please let me know. That would be really exciting, actually. No, it is not ruled out. In the worst case, what we're seeing is that inflation is actually internally inconsistent. So we need to go back to the drawing board in some sense.
Yes.
Wasn't this all very specific to single field? What about like current house scenario?
Okay, so if I right. That's a good question. So if you add in scalar field, if you have a spectator field, or if you have all sorts of other fields, then what you have is the only physical difference between what's going on there and what's going on in what I showed and what you were suggesting is that you have entropy modes then. Okay? These entropy modes you can show enter in exactly the same way that the single field mode would. And in particular, their divergences are exactly the same. So it isn't, that doesn't say you at all.
Well, multi-field.
That's what I mean. So if you added, I mean, do you mean like just multiply coupled or coupled through gravity? Just minimally coupled? I guess it depends on their mutual coupling, but I'm saying minimally coupled additional fields will behave in the same way.
You're assuming something about the kinetic term. You're not
No, you mean one field is slowly rolling, or
Oh, to make it a little bit more extreme, let's take K inflation.
okay.
Okay, what about that?
For K inflation, I'm not exactly sure. But do you believe K inflation? I don't know.
Inflation.
Well,
You were saying that inflation is somehow.
no. Well, I mean, the basic mechanism of slow roll. Okay, I mean that's ubiquitous in inflation. There's a small gradient, to zero-like expansion. That's ubiquitous even in K inflation. That element of it is, I mean, the expansion of this infrared phase space, right?
Yeah, I just find two of your statements hard to reconcile. Namely, that you get such huge effects on the say the luminosity distance, and yet see no effect, say, on spectral index or anything else. That you seem to imply that there could be no effect, say.
No, I'm not making any definite claim as to what the actual effect would be. I can't rule it out. The point is that all I'm seeing right now from this effective calculation is that the perturbation theory is failing. Now, it could be that that's associated with some physics, but it could just also be that the actual assumptions that went into it are incorrect.
Now, from the last question to the very last question, Paul.
This is a very general question. Like, can one think of kind of classifying the background matrix and saying that, okay, for this background matrix, second order perturbation is going to grow. And for this other one, the first order is enough. I mean, this is probably a property of, at least in part, it's a property of the background matrix, isn't it?
I mean, there's certainly with the standard classical cases with linearization instabilities, you know that all backgrounds which are closed and have isometries have linearization instabilities. That does not imply that the next order is growing. My claim is that similar arguments do apply for slow roll, but it is in principle possible, but I don't think it's unique. Because you can always construct some crazy perturbation theory. My crazy perturbation theory is just the community's crazy one. That's what I've chosen to be my canonical one. But you can make an arbitrary perturbation theory.
Okay, so next time.